So, today we are going to discuss main questions from chapters 6, 7, 8, 9, 10 of plus 2. So, here you can see a question. In the figure shown, when the switch S is closed, one of the two bulbs glow momentarily. Which one is that? So, this question is from electromagnetic induction. Okay, so here uh, when the switch is turned on, either of these two bulbs are glowing. Which bulb is glowing? So let's see. If the switch is closed, okay, if the switch is closed, definitely current will be flowing like this. Definitely current will be flowing like this because the direction of battery is connected in such a way that the current is flowing in clockwise direction. So if you take the diode D1 and if you consider diode D2, induction will happen in the first circuit and current will try to flow in the opposite direction because according to Lenz's law it has to oppose the main cause. And if you take diode D2, induction will not happen. Why? Because the diode D2 is reverse bias, so the current cannot flow through this circuit. The current will not flow through this circuit and hence the bulb A will be glowing. So here electromagnetic induction, Lenz's law, Faraday's law, all these are important concepts. Okay, the next question is, the radius of a coil decreases steadily at the rate of 10 raised to minus 2 meter per second. A constant and uniform magnetic field of induction 10 raised to minus 3 Web per meter square acts perpendicular to the plane of the coil. What will be the radius of the coil when the induced EMF is 1 microvolt? Okay, so this is the question. So they have given some information. We have to calculate what will be the radius of the coil. This is what we have to calculate. So something which we know that is the formula for induced EMF. Induced EMF is equal to d phi by dt or minus d phi by dt. Just taking the magnitude, it is d phi by dt. Now flux is equal to magnetic field into area. Okay, magnetic field into area. So I can write area as pi r square. So what will be induced EMF? It will be d by dt of magnetic field into area, which is pi r square. Okay, now b and pi you can take common. The derivative of r square will be 2r dr by dt. 2r dr by dt will be the derivative of r square. So next is what we have to calculate is r. R is equal to induced EMF. Okay, induced EMF divided by 2 times b into pi into dr by dt. Okay, dr by dt. Now let's check the values which they have given. Induced EMF is given clearly it as 1 microvolt, so 10 raised to minus 6 divided by 2 times magnetic field. What is a magnetic field? 10 raised to minus 3 into pi into dr by dt. What is the value of dr by dt? They have given it as the radius of a coil decreases steadily at the rate of 10 raised to minus 2 meter per second. So dr by dt is 10 raised to minus 2. Substituting all these values, you get 5 by pi centimeter. So this is the correct answer, 5 by pi centimeter. So here you should know the formula for induced EMF. At the same time, you should know how to take the derivative, and that's what we have seen here. And then finally we calculated r. Dr by dt was already given, so there is no confusion and there is no unit changes. We don't have to convert anything, no conversions, so it's a direct substitution formula. Okay, this question is from alternating current. The question is, the equation of the current in AC circuit is I equal to 4 times sine 100 pi t plus pi by 3 ampere. We have to calculate all these things. So this question includes so many things that we can calculate. Actually, this question is easy. So let's first initially look at the formula. I equal to I max sine omega t plus or minus phi. This is a general equation. So what is this equation basically? This equation is instantaneous value of the current. Instantaneous. Okay, this is the instantaneous value of the current. Now let's compare this equation with the equation given in the question, and let's find out these unknown parameters. Looking at the equation itself, we can understand that I max is 4 because it's already given here in the question. It is I equal to 4 times, so I max equal to 4, which is the peak value. Okay, so 4 became the peak or peak value. Now omega is what? 100 pi. Okay, what is omega? Omega is also equal to 2 pi f. So by comparing 100 pi and 2 pi f, we will get the value of frequency. What will be frequency? You can equate 100 pi with 2 pi f and you get frequency as 50 hertz. So frequency also is ready. Peak value is 4. Okay, 4 is the peak value, frequency is 50 hertz. Now this phi is called as the initial phase. So by comparing from the above equation, we understood that pi by 3 is our initial phase. Now something is left out. Okay, so we got the third parameter. Something is left out is the RMS value. So what is the relation between RMS and maximum value? RMS equal to maximum value by root 2. Since in this question it is all about current, let's write it in terms of current. That will be I max by root 2. Fine. I max is also equal to I peak. So I peak by root 2. Now what is peak value? It is 4. So 4 by root 2. You can multiply with root 2 and divide with root 2 to get 2 root 2 as the answer for the RMS value. 2 root 2 ampere. Okay, so RMS is also fine. Finally, you have to calculate the current at time 0 second. For that, you have to directly substitute t equal to 0. That is 4 sine 100 pi times 0 plus pi by 3. This term will become 0. What is left out? It is 4 times sine pi by 3. 4 times sine pi by 3 is equal to 4 times root 3 by 2. Root 3 by 2, which will be equal to 2 root 3 ampere. That's how we will calculate all those parameters from one single equation. Remember, the given equation in the question is the instantaneous value of the current. Okay, in this question you can see a 50 watt 100 volt lamp is to be connected to an AC mains of 200 volt 50 hertz. What capacitance is essential to be put in series with the lamp? Okay, this is the question. So here initially they have a 50 watt 100 volt lamp initially. Now they have to connect that into a higher voltage. What will happen if that happens? If you are having a bulb which works in a lower voltage, and if you are connecting into a higher voltage, that particular bulb will burst off, correct? So what should I do in order for the bulb to glow even at higher voltage? You can connect a capacitor in series to it. So that capacitance will increase the impedance and thus it will balance the voltage. Okay, so the bulb which we are planning to connect into higher voltage will glow in the higher voltage. At the same time, we don't have any losses too. Why? Because I connected a capacitor. I can connect a series resistor also. Okay, see, a bulb which is working in 50 watts, okay, 100 volt. If I am connecting into a series resistance, okay, now let me take 200 volt source. I can do like this also, but what is the problem? The problem is this resistor will dissipate heat and the efficiency will decrease. So that is not what we require. We require something different. We require a capacitor to be connected there. So once you connect a capacitor, the advantage is the bulb will glow, and at the same time there won't be any loss of heat. So that is a concept we are using here. So 50 watts 100 volt 50 watts 100 volt bulb. Let me focus your attention to this particular value. Power is 50, okay, voltage is 100, from which you can calculate the value of resistance. How can we calculate? Because we know a formula, power equal to V square by R. So R will be equal to V square by P. Substituting 100 square by 50, you get the resistance as 200 ohms. So the resistance of this bulb is 200 ohms. Okay, that's the first point. Second point is the maximum current that should pass through this bulb is I equal to V by R. That is 100 volt divided by 200 ohm, that gives 0.5 ampere. So this should be the maximum current that should flow through this particular bulb. So even if you connect a capacitor in series with this bulb, at any cost, if current is flowing more than this 0.5 ampere, it will damage the bulb. So that should be always in mind. So what I am going to do now? Now I connect a capacitor in series. The question is, what should be the value of that capacitance in order for our bulb to glow properly? So in the second case, let me write V equal to I times Z. What is Z? Impedance. Why impedance came? Because along with resistance, if either capacitance or inductance term is coming, then we have to take the concept of impedance, because impedance includes resistance and reactance. It can be inductive reactance or it can be capacitive reactance. Now, what is the impedance it should be? What is the impedance it should have? Impedance will be equal to voltage by current. Correct? From this equation, Z equal to V by I. What is the new voltage? It is 200. What is the maximum current it should flow? It is only 0.5 ampere, from which we can calculate the value of impedance this circuit should have. That means the new circuit should have is 400 ohms. Now we know that impedance is equal to root of R square plus XL minus XC whole square. So since there is no inductance term here, let me write the capacitive reactance term. Now Xc is also equal to 1 by 2 pi Fc. Okay, 1 by 2 pi Fc, 1 by 2 pi Fc whole square. What is our impedance value? Our impedance value is 400. So by substituting, that means by substituting in the entire equation, that is 400 equal to root of, what is our resistance value? Our resistance value is 200 square plus 1 by 2 pi F is 50 into C whole square. So what left is to solve this part. Once you solve this entire thing, you get a value of capacitance C equal to 9.2 microfarad. So this is where you have to be very careful. That is the solving part. You have to carefully take the square on both sides, and then you have to calculate the capacitance. How I got F equal to 50? It's given in the question. It's given in the question that it should work in a 200 volt 50 hertz supply. So my frequency is 50. Understood? So that's how you can calculate the value of capacitance. Similarly, the capacitor can be replaced by an inductor too, but there will be a lagging issue. So lagging issue for the current. So we normally prefer capacitors in order to make a bulb glow at higher voltage. Okay, hope you got the question. A question from Ray Optics. I guess this is your favorite chapter, whatever. A concave mirror of focal length f produces an image n times the size of the object. If image is real, then the distance of object from the mirror is dash. So just read the question once again and think very carefully. We have a concave mirror. We have a concave mirror, got it? And its focal length is f, and it's producing an image n times the size of the object. It's given that the image is real. If so, what is the distance of object from the mirror? Means we have to calculate the value of u. Let's write what all things we know. Mirror formula 1 by v plus 1 by u equal to 1 by f. Magnification formula m equal to minus v by u. It is also equal to height of the image by height of the object. Now in the question it's clearly given that the image is n times the size of the object. So image is n times the size of the object, means n times HO divided by HO. Also it is given that the image is real, so it should be negative. Why? Because in order to get a real image in the case of a concave mirror, that image height will be calculated downwards. Downwards means below the principal axis. So concave mirror, if you keep somewhere here, and if you keep the object somewhere here, and you are getting an image something like this, that is why we are taking the value of n as negative, because it's a real image. Now from which we get minus, okay, I'll write over here, minus v by u equal to minus v by u equal to minus n. That's what we get, correct? That implies v is equal to n times u. Now what is our formula? 1 by v plus 1 by u equal to 1 by f. That means 1 by v, that is 1 by nu, plus 1 by u equal to 1 by f. Okay, solving this we will get the value f equal to, u equal to, the question is to calculate u only, so solving this we get u equal to f times n plus 1 divided by n. Okay, that's how we can solve this question. Another question from Ray Optics. Okay, focal length of a glass lens in air is 2 cm. Its focal length when immersed in water would be dash. We know something that a lens in air will be having one focal length, and once you keep that inside another medium, its focal length will change. Now, what will happen to the focal length of the lens once it is immersed in water? Will it increase or decrease? First, think about that. Okay, keep an answer in your mind. At least increase or decrease, or it will not change. Okay, 3 options are there. Now let's do the problem and let's find out the focal length of the lens once you keep it inside the water, and let's finally conclude what will happen to the focal length. So what all things are given? Focal length of the lens in air, it's given as 2 centimeter. Okay, now we know that refractive index in the case of air is equal to 1. So let's take as the first medium as air. Second medium, let's take it as glass, which will be having a refractive index of 1.5. Now why I wrote this is because we have a formula which is 1 by focal length is equal to n2 by n1 minus 1 into 1 by r1 minus 1 by r2. This is a very important formula which is a general formula, which is a generalized formula, so you have to study this. So here we know that the focal length in the air is 2. So once you substitute these values, that is 1 by 2 equal to n2 is 1.5 by 1 minus 1 into 1 by r1 minus 1 by r2. 1 by r1 minus 1 by r2. We cannot solve this equation because two unknowns are there. So let's put it as equation number 1. Now we need one more equation, right? That is why they have given the second case. That means the lens is immersed in water. So once the lens in water case comes, lens in water, what will happen? Okay, this is the second case. From second case also we will get an equation similar to the first case, and then it will be easy for us to solve. So how will you write? 1 by F water. 1 by F water is equal to, once again the same formula, n2 by n1 minus 1 into 1 by r1 minus 1 by r2, because r1 and r2 is not going to change because it is inbuilt, right? That is something which we cannot change, but focal length can change. Now what is the value that we have to substitute for this F water and all other things? N1 is equal to water 1.33, which is the refractive index of water. Now once it comes to n2 is equal to 1.5, which is the refractive index of glass. Okay, now let's write down the equation. So 1 by F water, that's what we have to calculate, right? Equal to 1.5 divided by 1.33 minus 1 into 1 by r1 minus 1 by r2. That will be our second equation. Now we can calculate for F water. Once you can calculate for F water, because F air was given, so the only thing that we have to calculate is F water. How can you do that? You can solve for equation 192. So simply by dividing, you can calculate the value of F water. So solving equations 192, you get F water, that is the focal length once it comes inside water. It will be 0.5 divided by 0.128 into 2 you will get, which will be equal to 8 centimeter. So what did we conclude? We concluded that the focal length which was in air, it was 2 centimeter, increased to 8 centimeter. So that's what will happen if you take a lens and you immerse that lens into a medium with higher refractive index. Its focal length will increase. Did you understand? Okay, this is a question from wave optics polarization part, especially Brewster's law. So how can we solve this question? The question is a simple question. A ray of light is incident on a glass plate at an angle 60 degree. What would be the refractive index of glass if reflected and refracted rays are perpendicular to each other? So they have indirectly asked the case of Brewster's law. So for that you should know what is Brewster's law. What is Brewster's law? You take a medium and imagine a light ray is hitting that medium, making an angle of incidence I, and some part of the light ray is getting reflected, and some part of the light ray, imagine it is getting refracted also. So let's write the angle of incidence as I, angle of reflection, let me write it as RE, angle of refraction, let me write it as RF. So some part will get refracted, some part will get reflected if it is a translucent material or medium. Now what's the point? Brewster's law says that in a particular angle, when the light ray hits the medium, the reflected light ray will be plane polarized. In some angle, when the light ray hits the medium, the reflected light ray will be plane polarized. Not only that, once that happens, the reflected light ray and the refracted light ray makes an angle of 90 degree. So these are the two observations, very important observations during Brewster's law. And one thing you can write in that particular case is the tangent of the polarizing angle. Polarizing angle means incident angle of incidence. So the tangent of the polarizing angle will then become equal to refractive index of the medium. Okay, that is what will happen. We have to calculate the refractive index of the medium. Directly we can calculate, since they have already mentioned that this is a Brewster's law case. How they have mentioned? Because they have told that the reflected and refracted rays are perpendicular to each other. This is an indirect method of saying that the question is from Brewster's law. So directly you can substitute the tangent of the polarizing angle, means polarizing angle is 60 degree, and tan 60 you can easily calculate, which is sine 60 divided by cos 60. What is sine 60? Root 3 by 2. What is cos 60? 1 by 2. And thus you get to root 3. That is one method. Now, another method is that if you don't know Brewster's law, then how can we solve this? Refractive index according to Snell's law is sine I divided by sine R. So we only need to calculate R. What is this R? Angle of refraction. Angle of incidence, it's already given, it is 60 degree. It is 60 degrees, so there is no confusion in that. Once you can calculate the value of RF, then we can calculate the refractive index. For that, they have given the hint that the angle between reflected and refracted light rays is 90 degree. So let's take this angle, let's take this angle. If you take this big angle, what will be the sum of all these angles? It will be 180 degree. So angle of reflection plus the 90 degree plus RF will be equal to 180 degree, from which you can calculate RF. RF will be equal to 180 minus 90 minus RE, that is equal to 90 minus RE. What is RE? Angle of reflection. Angle of reflection will be equal to angle of incidence 60 degree itself. So 90 minus 60 you get 30 degree. Thus angle of refraction became 30 degree. You can now substitute in the formula of refractive index sine I, which is 60 degree, divided by sine RF, that is angle of refraction, 30 degree, which would be equal to once again root 3. So this is the second way of doing the same problem even though you don't know Brewster's law. Okay, this question is from wave optics. In this question, first thing we have to understand is that we have to identify whether it is interference, diffraction, or polarization. So here it's given that light of wavelength 6000 angstrom is incident on a slit. That means one single slit is there. Of width is given. The screen is placed 2 meters from the slit, and you have to calculate the position of the dark fringe and the width of the central bright fringe. If you clearly remember the pattern of the diffraction, that means initially there will be a central bright fringe will be the followed by dark fringe, followed by bright fringe, but with a lesser amplitude on both sides. So that's how it goes. So we have to calculate the position of the first dark fringe, of the very first dark fringe, which means we have to calculate this distance x. So once you calculate this distance x, then in order to calculate the width of the central bright fringe, that will be nearly 2x. Okay, so that's what we are going to find out. So initially we find x, that is the position of the first dark fringe, and then we calculate the width of the bright fringe, which will be the double of this value, which will be 2x. So since it is the first dark fringe, we can substitute the value of n equal to plus or minus 1. Now capital D is the distance between the slit and the screen, which is given as 2 meter. The wavelength we are using is of 6000 angstrom, which I can write as 6 into 10 raised to minus 7 meter. Okay, now we know that once you study diffraction, we know that sine theta is equal to x by d. That means once you draw the entire figure of this diffraction pattern, there inside you get a triangle, right? In that triangle there will be a theta. So that sine theta will be equal to opposite side by adjacent side, and opposite side is the position. Something looks like this. If you do remember the triangle, it looks like this. This is the theta, and this will be x, and this will be d. Okay, so sine theta equal to x by d. Fine. Now what is a? The slit width. Slit width is equal to 0.3 millimeter. 0.3 millimeter, which will be equal to 3 into 10 raised to minus 4 meter. Now path difference a sine theta should be equal to n lambda. A sine theta should be equal to n lambda. That is, a times sine theta is x by d equal to n lambda, from which we can calculate the position of the first dark fringe in diffraction. Okay, in diffraction. In interference it is different, n lambda d by a. So in interference it will be different, and here diffraction we are using this condition x equal to n lambda d by a for calculating the position of the dark fringe, and this x equal to you substitute values plus or minus 1 into lambda 6 into 10 raised to minus 7. Okay, now d is 2 meter divided by 3 into 10 raised to minus 4. What you get is a value which will be plus or minus 4 into 10 raised to minus 3 meter. Okay, that's the answer for the first part. The answer for the second part, as I told, we only have to calculate 2x, because that is the width of the central bright fringe, and the answer will be 8 into 10 raised to minus 3 meter, or 8 millimeter is the final answer. So always you have to refer to the formula connecting the interference, diffraction and polarization. There might be a big confusion in the formula in the case of interference and diffraction, which you have to be careful. Okay, fine. This is a question from electromagnetic waves. Okay, yeah. The two chapters that we normally don't give much importance is electromagnetic waves and communication, but still questions can come from these chapters. And electromagnetic waves, as you consider, it's not so easy chapter 2. Whenever we hear about electromagnetic waves, we might be thinking about the spectrum only, that is why. But actually there are problems which are very important inside the chapter electromagnetic waves. Let's see a question from it. In an electromagnetic wave, the amplitude of electric field is given. The frequency of the wave is given. The wave is propagating along the z-axis. The average energy density of electric field in joule per meter cube will be dash. So many things are given and we have to calculate the average energy density of the electric field. So let me write few formula regarding that. Average energy density due to electric field is U times UE equal to half epsilon 0 E square. Okay, this is what we need to calculate in this question. So directly we cannot go and substitute electric field as 1 volt per meter. That is what we have to be careful, because half epsilon E square you have to rewrite it as E0 by root 2. E0 by root 2 square. Okay, that gives you 1 by 4 epsilon 0 E0 square. Now you can substitute electric field the value which is given. Okay, do not substitute in the electric field which is in this formula. Okay, that's the first thing we have to notice. So yes, for this question if you substitute electric field value then epsilon 0 value, you get the answer. But okay, we'll do that first. So you get 1 by 4 times epsilon 0 8.854 into 10 to the power minus 12, okay, into E0 value which is 1 square. You get an answer of 2.2 into 10 to the power minus 12 joule per meter cube you will be getting. Okay, so in the question they have asked that much only, fine. What if they are asking the average energy density of the magnetic field? What is the formula? In that case, average energy density due to a magnetic field formula is 1 by 2, okay, mu 0 in the denominator, 1 by 2 mu 0 in the denominator into b square in the numerator. Now b you have to substitute, that is 1 by 2 u0 mu 0 into b0 by root 2 whole square. This is the average energy density due to magnetic field. What will be that? It will be equal to 1 by 4 mu 0 in the numerator, it will be b0 square. Is it correct? Yes. So that is the average energy density due to magnetic field. Now if the question is asking simply average energy density, then we have to calculate the sum of these two. If they are asking simply average energy density, you have to calculate the sum of average energy density due to electric field and average energy density due to magnetic field. That gives you an answer of 1 by 2 epsilon 0 E0 square, which is also equal to 1 by 2 mu 0 b0 square. Both are same after adding. The reason is why, because electric field energy density and magnetic field energy density both are same. Okay, so once you calculate the average energy density, you have to calculate the sum of these two. So but at the same time, electrical average density due to electric field and average energy density due to magnetic field is same. So you get the sum as this: half epsilon 0 is 0 square, 1 by 2 mu 0 b0 square. Remember the unit, it is joule per meter cube is the unit of average energy density. Now there are formula regarding Poynting vector, radiant flux density, okay, radiant flux of electromagnetic wave, momentum of the electromagnetic wave, intensity of the electromagnetic wave. All these are some hidden formula in this chapter which we never notice. So you have to refer all these formula, okay, fine. Now in this question, a point source of electromagnetic radiation has an average power output of 800 watts. The maximum value of the electric field at a distance 3.5 meter from the source will be dash. You have to calculate the maximum value of the electric field at a distance. The distance is 3.5 meter from the source. Now there is a formula connecting this, which I have told in the previous question. I told that there are so many other things to study in the electromagnetic waves chapter. One is intensity of electromagnetic wave. So we might not be studying all these things in theory, but definitely we have to consider this formula in entrance point of view. Now what is that intensity of electromagnetic wave? The energy of electromagnetic wave crossing per unit time per unit area perpendicular to the direction of propagation of wave is called the intensity. Okay, I'll say it again. The energy of electromagnetic wave crossing per unit time per unit area perpendicular to the direction of propagation is called the intensity of electromagnetic wave. What is the formula for it? Intensity of electromagnetic wave is equal to average power divided by 4 pi r square. Okay, now why we need to calculate intensity? Here we are not going to calculate intensity, we are going to calculate the electric field. Now why did I write intensity? Because intensity is a formula that is connecting the electric field. You can see over here, it is equal to half epsilon 0 E0 square into velocity of light. That is, if you do remember, average energy density into velocity of light. We studied in the previous question as this value as average energy density, total average energy density. Okay, now that is half epsilon 0 E0 square into C, which you can also write as 1 by 2 mu 0 into B0 square into C, because this term is also average energy density, total average energy density. I told you we can write in the terms of electric field and magnetic field also. There is an independent formula for average energy density for electric field. There is a formula for average energy density, total average energy density in terms of electric field and magnetic field. Don't get confused. If you have doubt, you can check the previous question again. Then also you can write this term as 1 by 2 mu 0 into E0 square by C. You can write in different ways what intensity. Now what is the formula for C? C is the ratio of electric field to magnetic field, velocity of light. It is also equal to 1 by root of mu 0 epsilon 0. So these are different formula that is connecting with this chapter. Still the formula is not yet complete. I mean, there are many other formula pending in this chapter which you can refer later. Okay, so you might be having a confusion how this formula came. For that, as I already told, you can substitute for B0. In this equation you can substitute for B0. What is B0? Now you can write B0 equal to E0 by C. So substituting for B0, which is E0 by C, which came from this equation, you will get this one. Okay, so we have these set of formula. Now I am taking only two from it, which is average power divided by 4 pi r square is equal to the formula which I wrote in the end, which is E0 square divided by 2 times mu 0 c square. Okay, and we need to calculate the maximum value of the electric field, which is E0, maximum value. So E0 is equal to root of, you solve this equation, you come to a conclusion which is equal to root of mu 0, okay, into C into average power divided by 2 pi r square, 2 pi r square. What next you have to do is a careful substitution for what is the value of mu 0? Permeability, right? It is 4 pi into 10 raised to minus 7. Velocity of light, it is C equal to 3 into 10 raised to 8. Average power, it is given as 800 watts. Average power, it is given as 800 watts. Then what else? Then radius r equal to 3.5 meter. So once you substitute all these, you get the value for the maximum value, the value of electric field, as you get it as 62.6 volt per meter as the final answer. Okay, that's how we do this problem. Okay, something extra that I have to tell to you regarding electromagnetism is the formula that is connecting all these electric field, magnetic field and all. So let me write the Ampere's circuital law, which is closed integral B dot dl equal to mu 0 I. Mu 0 I. Okay, we know that this is the Ampere's theorem. Fine. Now Maxwell found an issue in that. Maxwell found that it's not working properly. This equation is not working properly once a capacitor is coming into the circuit. So for all other cases, you can calculate the magnetic field due to Ampere's circuital law, because that's a very fine formula. But once a capacitor is coming into action, then it's not working. So Maxwell found that if a charge with a velocity gives a magnetic field, then a charge with changing velocity should give changing magnetic field. Okay, also he understood that the magnetic field from changing electric field is also possible. Why? Because in this equation, in Ampere's equation, what we are concluding in Ampere's circuital law? Ampere's circuital law is giving you the total magnetic field, correct, over a closed surface, over a closed loop. It's not surface, closed loop. Now if you remember Gauss theorem, magnetic field over a closed surface, closed integral B dot ds, that is 0. Okay, over a closed surface, magnetic field will be 0. So we don't have much use with the Gauss law, because every time you get the answer 0 only. And there is one more formula connecting magnetism, which is the first formula that we are studying, is Biot-Savart's law. Biot-Savart's law gives the magnetic field due to a very small piece of conductor, current carrying conductor, which will be equal to mu 0 by 4 pi ideal sine theta by r square. Did you understand? Ideal sine theta by r square. But again, this formula is Biot-Savart's law. Fine, Biot-Savart's law. But again, the problem is we can calculate only magnetic field due to a very small conductor of length dl. After that we have to integrate it. But the advantage is for Ampere's circuital law,
which is the already the integral form. And that is why we use Ampere's circuital law in many places. But what is the disadvantage? The disadvantage is it cannot, this formula we cannot use when capacitors are coming into play, action. Now Maxwell corrected that equation as integral B dot dl is equal to, okay, magnetic field over a closed loop is equal to mu 0 times I, let it be the, plus there is an extra factor which is mu 0 epsilon 0 d phi by dt, and this flux is electric flux. Okay, so varying electric field is actually creating magnetism. So magnetism from electric current and changing electric field, that is what we are writing here. Magnetism due to electric current and varying electric field. Now there is another formula which we have studied initially, which is Faraday's law. Faraday's law is integral E dot dl, close integral E dot dl is equal to minus d phi by dt. In that formula the flux is magnetic flux. So what is Faraday's law saying? Faraday's law says that a changing magnetic field gives electric field. Changing magnetic field gives electric field. Okay. Now that is the importance of Faraday's law. Changing magnetic field will give you electric field, and on the other side we have changing electric field is giving magnetic field, which is the formula of Maxwell. So all these formula are interconnected. Okay, if you see the timeline of it, it's like it's a very complicated timeline actually. It starts all from we have Ampere, we have, then in Faraday's law is coming later on, Gauss law is coming in history. If you check the history, it's like that. Then comes Maxwell. Even though we all say it as Maxwell's equation, a person we never should forget is Heaviside. The reason is because Heaviside is the actual person who actually brought all these equations together. And at that time we used to call Maxwell's Heaviside equations, but later on Heaviside, the name itself is we forgot, and we came to one single name, James Clerk Maxwell. Understood? So don't forget this eminent personality who has contributed a lot to combine all these equations of electricity and magnetism together to one single concept, which is electromagnetism. Okay,
Here you can see the Faraday's law simulation. Okay, the first simulation that we are going to introduce in the capsule classes is the Faraday's law. Here you can see a coil, a bulb connected to it, and a bar magnet. We all know what is going to happen as you introduce the bar magnet into the coil. What will happen once you introduce the north pole of the bar magnet into the coil? Definitely the bulb will glow. Fine. Now I am going to take completely that bar magnet through the other side itself. So south will be leaving. Once again the bulb is glowing. I don't know whether you noticed the direction of the needle. So I'll do it again. I am going to introduce the north pole of the bar magnet into the coil. Check the direction of the needle. Okay, direction of the needle is going towards left. Now I am going to take the south out from the coil. So direction of needle is towards right. I'm going to insert south into the coil from the other side, from this side. So south, when I introduce, it's going towards left. And once I take the bar magnet out entirely from the coil, that means north taking out from the coil, you can see the needle going towards right. So that is a case of a single coil experiment. Once I introduce two coils in which one is having lesser number of turns, what could be the expected result? The expected result will be the brightness of the bulb. In the case of only two turns, you can see the brightness is reduced. See, the brightness is reduced. But in the case of much number of turns, the brightness is more. You can feel the difference now itself. Understood? So brightness is decreasing or increasing depending upon the current that is flowing. Current means induced current. So whenever you introduce a bar magnet into a coil, actually electromagnetic induction is occurring, and that induced current is actually flowing through it, deciding the brightness of the bulb. Okay, so introducing field lines, you can see from north to south field lines will flow, and this is just to show you with field lines, nothing much other than that. And in the case of two turns, you can see the brightness is less compared to the previous case. Okay, so that's how you need to study a particular experiment. Via simulations you get a much better idea. I'll be introducing more simulations in the next classes. Okay, so I believe you understood today's class properly, and we will be discussing more questions from remaining chapters in the next capsule classes. Okay, thank you.